So you know data set is consisting of 6 chapters starting from array, stacks, stacks and queues, linked list, trees, hashing and graphs. Okay. So first I am giving priority to tree concept because most of the questions are coming from trees and then hashing and then graphs concept. That's why first I will finish these 3 topics. Afterwards I'll move to the remaining topics like arrays, stacks and linked list. Okay. So in tree concept mostly you can focus on some areas where the first topic is properties of trees. Like we'll discuss binary tree, binary search tree, AVL tree. Okay. So each and every tree we have several properties. We need to recall all those properties. After properties of trees, next we want to discuss tree traversals. Tree traversals like in-order traversal, pre-order traversal, post-order traversal, right? Afterwards we have to construct a unique binary tree by using in-order and pre-order, in-order and post-order, right? So after tree traversals over, next we are going to discuss another topic is called binary search tree. Afterwards AVL tree. AVL tree. So fifth topic, like we going to discuss time complexities based on various operations. Like inserting a node into AVL tree, how much time complexity will take? Deletion of node from AVL tree, how much time complexity will take? What is the time complexity construction of AVL tree by using n elements? So all these time complexity will be covered here. Okay. So that's all. These are 4 different topics where they are frequently asking in trees concept. So first we'll start with the properties of trees. By taking questions, I'll explain properties of trees, friends. Okay. By taking questions, I'll explain. So when we are talking about properties of tree, we need to recall the symbols also. Like for example, if n indicates total number of nodes, n indicates total number of nodes, and I indicates number of internal nodes, H indicates height of the tree, where L indicates number of leaf nodes. Then we want to discuss properties of various types of trees based on these parameters. Okay. So when you are talking about various trees, the first one, suppose if you ask total number of nodes in a binary tree, the total number of nodes in a binary tree depends on the structure of the binary tree. Therefore, if the tree is skewed binary tree, or if the tree is full binary tree, or tree may be having structure like this. Okay. If you observe all these trees and every tree is having height is equals to 2. Height equals to 2. Height means longest path from root to leaf node is called height. So height of the tree is equals to 2 here, height of the tree also 2, and that height of the tree also 2 only. In this case, how many number of nodes are possible in first example? In first example, number of nodes n is equals to 3 are possible. Number of nodes n is equal to 3, whereas in this case number of nodes n is equals to 7, where here number of nodes n is equals to 5, right? But height of the tree remains same, that is for h is equals to 2. For height h is equals to 2. So whenever height h is equal to 2, minimum here 3 nodes are possible and maximum 7 nodes are possible, or it may be oscillating between minimum and maximum. So minimum is possible if it is skewed binary tree and maximum is possible if it is a full binary tree. Then what is the relation with respect to parameter means, see, this 3 we can write it as h plus 1, h plus 1. So therefore n is equal to 3 we can write it as h plus 1. Whereas n is equals to 7, we derived formula in the classroom by taking geometry progression. For example, if I consider here number of nodes are 1, 1 means we can write 2 power 0, and at this level there are 2 nodes are there, therefore we can consider as 2 power 1, and at this level there are 4 nodes are available, we can consider as 2 power 2. Therefore, total number of nodes here 2 power 0 plus 2 power 1 plus 2 power 2. That is for n is equals to, for h is equal to 2, we are writing total number of nodes. This is equivalent to 2 power 0 plus 2 power 1 plus 2 power 2. Right, friends? This is analysis for h is equals to 2. If we take for h is equals to h, we can make it as 2 power 0 plus 2 power 1 up to so on plus 2 power. If I consider h is equals to 2, I stopped at 2 power 2. If I take h is equal to h, we can stop at 2 power h. So, which is equals to, it is following geometry progression. In geometry progression, sum of h plus 1 terms a into r to the power of h plus 1 minus 1 by r minus 1, which equals 2 power h plus 1 minus 1. Right, friends? Okay. So, therefore, minimum number of nodes are h plus 1 and maximum number of nodes are 2 power h plus 1 minus 1. Based on this topic, there are frequently asking questions in the gate paper. Okay. So, therefore, we can make the relation, the first property, if n indicates total number of nodes, then minimum how many possible? Minimum h plus 1 nodes are possible. Maximum how many possible? 2 power h plus 1 minus 1 are possible. Minimum means skewed binary tree, max means full binary tree. So, that is the first property you have to understand. And the second property, if you are talking about number of internal nodes, so number of internal nodes again depends on the what type of tree it is. For example, if it is skewed binary tree, number of internal nodes means root node also internal node, and this is also internal node, whereas this node is called leaf node, leaf node. So, here there are 2 internal nodes are possible. Therefore, 2 means I can say height of the tree, correct? Height of the tree, we can say h. Height is equal to, and number of internal nodes also 2. Therefore, h less than or equal to I. And if you take full binary tree in this format, then number of internal nodes are 1, 2, 3. So, 3 nodes are possible, internal nodes. So, instead of saying 3, we can say 2 power 0 and then plus 2 power 1. If I take h is equals to 2, we are taking 2 power 0 plus 2 power 1. If I take h is equal to h, we can take it is 2 power 0, 2 power 1 up to so on 2 power h minus 1 we can take. Right? It means that what I am trying to say, if you take h is equals to h, we can say 2 power 0 plus 2 power 1 plus 2 power 2 up to so on just before the last level, that is 2 power h minus 1. Clear, friends? Because if I consider last level, it is indicating total number of nodes. Therefore, 2 power h minus 1. Again, by summing up these values, a into r power h minus 1 by r minus 1. Okay. So, therefore, in this case, total number of nodes are 2 power h minus 1. This is indicate total number of internal nodes. For h is equals to 2, you can substitute here. H equal to, so 2 power to 4, 4 minus 1, that equal 3 nodes are possible. Next one, total number of nodes are completed, internal nodes completed. Next, we are talking about leaf nodes with respect to h. Third property, if it is skewed binary tree, number of leaf nodes are only one node here, right? Only one leaf node. Whereas, if it is a full binary tree, number of leaf nodes are 2 power 2. 2 power 2 indicates that 2 power h. Therefore, I can say only one leaf node is possible and max number of leaf nodes are 2 power h. Right, friends? 2 power h. So, that's all. This is a relation among number of nodes and number of internal nodes and number of leaf nodes with respect to height of the tree. Clear, friends? Okay. And the second one is we can also express height in terms of number of nodes. Okay. That point also I will discuss now. And fourth property, if I consider, suppose if you are considering a tree which is left skewed binary tree and then full binary tree and also if I consider complete binary tree. You know, complete binary means all levels are full except possibly last level filling from left to right. That is called complete binary tree. Okay, so all these trees are having height is equals to only, height equals to 2. So how do you express height in terms of number of nodes? In this example, height h is equals to 2. Here also height h is equals to 2. In this case also height h is equals to 2. Then how do you express height in terms of number of nodes, friends? Okay, whenever I am calling h is equals to here number of nodes. For example, here you can consider this value minimum height and then maximum height. You can take this relation, from that relation you can derive the values. Okay, so in this case, and h is equals to, I can say n minus 1. Number of nodes are 3 nodes, 3 minus 1. Therefore h is equal to n minus 1. Whereas in this case we know that 2 power h plus 1 minus 1 is equals to n, because total number of nodes is equals to 2 power h plus 1 minus 1. Since I want a h value, I can bring like this, 2 power h plus 1 is equals to n plus 1. Right, from this h plus 1 is equals to, bring to this side, it is acting as log base 2 of n plus 1. Right, friends, from this we can say h is equals to log base 2 of n plus 1 minus 1. It means that minimum height and maximum height, if you are talking, minimum height is possible if more number of nodes are there at each level. Maximum height is possible if it is taking skewed binary tree. Okay, so therefore log base of n plus 1 minus 1, here it is n minus 1. This is minimum height, this is the maximum height in a binary tree. So therefore you can say relation is minimum height of the tree and maximum height of the tree. Minimum height is equals to log base 2 of n plus 1 minus 1. Log base 2 of n plus 1 minus 1 is the minimum height, and maximum height is equals to, maximum height is equal to n minus 1. That is possible only by using skewed binary tree. N minus 1. So generally this height concept we are discussing with respect to complete binary tree, because most of the heap tree applications like inserting element into heap tree or deleting element from the heap tree, most of the operations based on only complete binary tree. Therefore we have to focus on complete binary tree maximum height, complete binary tree minimum height. So when you are talking about a complete binary tree, the complete binary tree having structure in this format. See here, it is a complete binary tree of height 2. Right, friends, I can also take complete binary tree of height 2 in this way. It is also complete binary tree. Complete binary tree means all levels are full except possibly last level filling from left to right. Last level filling from left to right. Here also it is filling from left to right, but it is not a complete binary tree. Therefore complete binary tree point of view, minimum what is the height and the maximum what is the height, that's what we want to discuss now. Okay, so I hope these points are clear. When it comes to complete binary tree, friends, just observe, minimum means up to height h minus 1 it is taking full binary tree, up to height h minus 1 is taking full binary tree, and extra one more node it is taking, correct? Whereas maximum is nothing but all levels are completely full, all levels are completely full. Therefore how you are interpreting this statement now? This is a formula for maximum number of nodes in a complete binary tree, right? That is a formula for maximum number of nodes in a complete binary tree. So when I am talking about a minimum number of nodes, I have to consider this case, minimum number of nodes. In that case, I want to remove this total part, friends. Okay, right? In complete binary tree, if I consider n indicates total number of nodes, the total number of nodes are maximum 2 power h plus 1 minus 1. It is possible it is fully occupied. So by using this approach, 2 power h plus 1 minus 1. And minimum number of nodes are, it is taking up to h minus 1 plus extra one more node it is taking. It means that we can say that is nothing but minimum number of nodes 2 power 0 plus 2 power 1 plus 2 power 2 plus up to so on 2 power h minus 1. It is taking only up to last level, and last level we have only one node, that is plus 1. It is taking sum of h terms, so that is a into r power h minus 1 by r minus 1 plus 1. So minus 1 plus 1 get cancelled, we will have 2 power h. Therefore, minimum number of nodes are 2 power h and max number of nodes are 2 power h plus 1 minus 1. By using this we can derive what is the minimum height, what is the maximum height. So by equating these two, 2 power h less than or equals to n, from this we can say h less than or equals to log n base 2, that is the minimum height, maximum height. By equating these two, we will get minimum height, that is same as which we completed here, log base 2 of n plus 1 minus 1. Therefore, in complete binary tree, it is having property, fifth property. Therefore, in complete binary tree, fifth property, maximum height is bounded by log n base 2, whereas minimum height is bounded by log base 2 of n plus 1 minus 1. So, in the exam, if they ask question, what is the maximum height of complete binary tree? Maximum height of complete binary tree is log n base 2 only. If they ask maximum height of tree, maximum height of binary tree, which is not a complete binary tree, in that case you can take n minus 1. Clear friends, okay? Repeating once again, in the exam paper if they ask what is the maximum height of complete binary tree, maximum height of complete binary tree is log n base 2. Whereas maximum height of binary tree is n minus 1. Similarly, minimum height of binary tree, either it is complete binary tree or full binary tree or skewed binary tree, it is taking log base of n plus 1 minus 1. Okay. So these are five important properties you need to remember. So based on these properties we have many questions friends. Okay, we will discuss those questions also. Just look at this one. A binary tree T has n leaf nodes. The number of nodes of degree 2 in that tree. Number of nodes of degree 2 in that tree. It's the most important topic friends. Okay. Because based on these topics there are so many questions are there, so many questions, minimum 5 times they ask this question in the gate paper. So a binary tree T has n leaf nodes, the number of nodes of a degree 2 in that binary tree is, okay. You also think about this problem, meanwhile I will derive one formula. You also think about this problem. So to answer this question, first you need to understand KRY tree. KRY tree. KRY tree means every internal node contains exactly k children. In KRY tree, every internal node contains exactly k children. For example, if I consider a tree of this format, so there are 3 internal nodes. Every internal node contains exactly 2 children. For example, see, this is internal node having 2 children, correct? This internal node is having 2 children. This internal node is having 2 children. So every internal node is having 2 children. That's why this tree is called 2ARY tree. If every internal node is having exactly k children, that is called KRY tree. If every internal node is having 2 children, that is called 2ARY tree. And if I consider another example, so in this case, every internal node is having exactly 3 children. So for example, here root node has also internal node, there are 3 children, and for this node also 3 children like this. Every internal node is having exactly 3 children. So this type of tree is called 3ARY tree. 3ARY tree. I can also draw 2ARY tree in this format. It is also called 2ARY tree. Because every internal node is having exactly 2 children, that's why it is called 2ARY tree friends, okay. So this is the way you need to understand the definition of KRY tree. Now how this definition is related to the current problem? Actually here they are asking about only binary tree, but I want to derive this formula for any type of tree, not only binary tree, okay. It may be 3RY tree or 4RY tree, what it may be. For every binary tree I need to derive the formula. This formula is the most important formula friends, okay. So suppose if I say that if there are if there are I internal nodes, I number of internal nodes, L number of leaf nodes, in a complete K-array tree, in a complete K-array tree, then what is the relationship among internal nodes and then leaf nodes? So clearly I number of internal nodes are there and L number of leaf nodes are there, and it is a complete K-array tree, and what is the relation between leaf nodes and internal nodes? Okay. Now for understanding that point, just observe, I am going to derive one important point here, that is, suppose if you take total number of nodes is equals to, in this example, how you will get total number of nodes? There are three internal nodes. First internal node, it is second internal node, it is third internal node. Right friends? There are three internal nodes. Therefore, I am writing three internal nodes. Each internal node is contributing two children. For example, with respect to root node, these are two children. With respect to this node, there are two children. With respect to this internal node, these are two children. So each internal node is contributing two children. That's why 3 into 2 children. Plus one node is missing in the counting. Who is that? Means root node. That's why I am taking plus 1. Okay. Where this 3 indicates that number of internal nodes. Number of internal nodes I defined it as I. Right friends. This 2 indicates that number of children for each internal node. Number of children for each internal node I am taking it as K-array tree. K-array tree means that equals to every internal node is having K children. Therefore K-array tree plus 1. Right friends. I into K plus 1. Whereas actually total number of nodes we can also write it as number of internal nodes plus number of leaf nodes. Just total number of nodes means internal nodes plus leaf nodes. I want to make the relationship between leaf nodes and internal nodes and K-array values. Therefore, number of leaf nodes is equals to, by bringing I that side and taking I as common, I into K minus 1 plus 1. This is the most important relation which is useful for solving many problems. Okay, many problems we can solve. So number of leaf nodes is equals to number of internal nodes into K minus 1, where K stands for K-array tree plus 1. Clear friends? Okay. Now in this example, just observe, a binary tree has n leaf nodes, means they already provided there are n leaf nodes, right? And the number of nodes in a degree, number of nodes of a degree 2 in tree. Actually the number of nodes of degree 2 they are asking. Number of nodes of degree 2. I don't know how many nodes are there, just that is the reason I am taking, let I1 is equals to number of nodes of degree 1, where I2 is equals to, I am taking it as number of nodes of degree 2, number of nodes of degree 2. So therefore, according to previous formula, total number of nodes n is equals to, number of internal nodes into K-array tree K plus 1. But total number of nodes is nothing but internal nodes plus leaf nodes, right? Therefore, we are writing it as number of internal nodes plus leaf nodes is equals to I into K plus 1. Correct friends? I into K plus 1. But in a binary tree, there are two types of internal nodes. What type of internal nodes? Two types of internal nodes. What are they? Internal nodes of degree 1, internal nodes of degree 2. Right? Internal nodes of degree 1, internal nodes of degree 2. Therefore, this I indicates that there are two types are there. I1 type of internal nodes plus I2 type of internal nodes plus L is equals to, here I indicates I1 internal nodes, where each internal node of degree, how much degree? 1. Means every internal node is having 1 degree. Therefore, I1 into K plus again I2 internal nodes of degree 2. Therefore, I2 into 2 plus 1. Right friends? So from this I want to find number of leaf nodes. Therefore, I1 into 1, here also I1 into 1 get cancelled. Therefore, L is equals to 2I2 minus I2, that equals to I2 minus 1. What do you mean by I2? I2 indicates that number of internal nodes of degree 2. number of internal nodes of degree 2. So therefore, in this problem, in a binary tree, T has n leaf nodes. Therefore, in the place of L, they mentioned it is n leaf nodes. Please understand, n leaf nodes, friends. Okay, n leaf nodes. Here I have taken n is equal to total number of nodes. Please understand, it is total number of nodes. Total number of nodes. Here I am taking total number of nodes, right? Where total number of nodes means internal nodes plus leaf nodes, right? From this here, L is equals to I2 minus 1, but in the given problem, n indicates total number of leaf nodes. That's why I am taking L is equals to n, which is equals to I2 minus 1. Actually, what do you want here? The number of nodes of degree 2, they are asking, number of nodes of degree 2. So, number of nodes of degree 2 means obviously that equals to I2. I2 indicates number of nodes of degree 2. Therefore, I2 is equals to, actually here it is plus 1, right? I2 plus 1 to I2 plus 1. So, bring I2 is equals to n minus 1, right? What is n indicates here? Not total number of nodes. In this particular problem, they mention n is equal to leaf nodes, friends. Okay. Generally, we are taking n is equal to total number of nodes, but in this particular problem, they are taking n is equal to leaf nodes. So, only remember I2 is equals to n minus 1. Okay. What is n indicates? N indicates number of leaf nodes. This model question asked in 5 times in the gate paper. It is one question. Okay. One time they ask question, there are 200 leaf nodes are there. Okay. There are 200 leaf nodes are there. Then how many number of nodes of degree 2 are possible? How many number of nodes of degree 2 are possible? Simple answer, that is 200 minus 1, that equals to 119. And one time in the gate paper they are asking, there are 20 nodes are there of degree 2. Okay, there are 20 nodes are there, sorry, there are 20 leaf nodes are there. How many number of nodes of degree 2 are there? Answer is 20 minus 1, that equals to 19. So basic idea is you have to remember, number of internal nodes of degree 2 means number of leaf nodes minus 1. Okay. So I will show those questions also, you will get more clarity. See here, a binary tree T has 20 leaf nodes. The number of nodes in T having 2 degree, 2 children. So it is indicating that is 20 minus 1. That equals to 19. Yes, there are 200 leaf nodes are there. Therefore, answer to this question is 200 minus 1, that equals to 119. Right. So this is the first model you have to understand, friends. Many questions came from this model. Please remember this model. Next one. This is regarding post order traversal. So which of the following sequence denotes the post order traversal sequence of the tree of the above question? Actually, question is missing actually. So I want to explain how to find post order traversal, pre order traversal, in order traversal in shortcut method. Try to understand. You can find this type of question in the gate paper. Okay. So for example, if I consider a tree, this question is not related to the given question, friends. Randomly I have taken one diagram, but I am explaining model questions, friends. Okay. So in binary tree, for every node, we need to maintain left child pointer and right child pointer. So node structure is looking like this. If I consider node A, so for node A, left side is pointing to left subtree, it is pointing to left subtree, and right child is pointing to right subtree. So we can say it is a node, it is left pointer, it is right pointer. Left pointer is pointing to left subtree and right pointer is pointing to right subtree, friends. Therefore, whenever you are traversing a tree, in tree there are, while traversing tree, just observe, first time you are touching node and then you are moving like this and you are coming back and you are touching second time. Afterwards you are completing right subtree and you are coming back to this place, this is the third time. Means every node we are touching 3 times, friends. Okay, 3 times. So based on the touching method, how to write pre-order traversal, in-order traversal, post-order traversal. So pre-order traversal and second one in-order traversal, third one is post-order traversal. Exam point of view, it is easy to apply in-order, pre-order, post-order. So this is a model question, GATE 96 model question, friends. They provided one diagram. They're asking which of the following sequence denotes post-order traversal of the above tree. Actually, the tree is not printed here. I'm taking one random tree to explain this concept. Okay. So whatever answer you are getting here, this answer is not related to this question, friends. Please observe. So pre-order traversal means, so whenever you are traversing the tree, it is first time you are touching, right? First time. When you touch first time, you can write in pre-order. Afterwards, you are traversing towards left subtree. So actually leaf nodes are not having any subtrees. That's the reason we are making them as null pointers or null links. Let us start traversing the tree. Pre-order traversal, and then in-order traversal, and then post-order traversal. So pre-order traversal means when you touch first time you print in pre-order, and when you touch second time you print in in-order, when you touch third time you can print in post-order. So now traverse the tree starting from A. It is first time you are touching that node, therefore write in pre-order traversal. Second time you are touching, write in pre-order traversal. Sorry, first time you are touching B. It is first time you are touching B, D, write in pre-order traversals. Right, friends, okay. Afterwards, you are second time touching this node, then write in order traversal. In order traversal. Afterwards, it is a null link. Third time you are touching this node, write in post order traversal. Right, continue this process for remaining nodes. So when you touch second time in order traversal, when you touch first time, it is pre-order traversal. Second time, which is in order traversal. Third time, which is in post-order traversal. Third time, which is in again post-order traversal. Second time, and then first time. Second time means in order traversal. First time means pre-order traversals. Again, first time pre-order traversal. Second time and then third time. So F. Second time in order traversal. First time and then second time. So first time, that is in pre-order traversal. Second time in order traversal. Third time. Again third time. It is again third time. Right, friends, okay. So this is pre-order, in-order, post-order traversal. You can apply this logic for all trees, friends, okay. So that you will get concept about pre-order, in-order and post-order, okay. I hope this model is clear now, right. Yeah, these are regarding properties of binary tree, just now explained. They are asking which of the following statement is false. Just observe, a tree with n nodes has n minus 1 edges. Obviously it is true, because every tree must contain n minus 1 edges, otherwise the tree become disconnected. In the spanning tree concept also I clearly explained, in a graph with v vertices it must have v minus 1 edges, right. So therefore first statement is true. Next, a label rooted binary tree can be constructed uniquely given post order and pre-order. Actually, we cannot construct unique binary tree with the help of post order and pre-order. Please understand, okay. We cannot construct unique binary tree with the help of pre-order and post-order. Then how we are constructing unique binary tree means we can construct by using in-order and pre-order and in-order and post-order. Unique binary tree is possible by using in-order plus pre-order combination. Another one is in-order and post-order combination. Clear, friends? Unique binary tree is possible by using in-order pre-order and in-order post-order. But in the exam, if they ask unique full binary tree, full binary tree means every internode is having exactly 2 children, right? So, for example, if they ask unique full binary tree, so if they ask unique full binary tree, yes, then it is possible by using in-order plus pre-order and also it is possible for in order plus post order, and even it is possible for pre-order plus post order. You should remember these points, okay? If they ask unique full binary tree, it is possible to construct by using these combinations, okay? So why it is not possible to construct only in order traversal and only pre-order task means, you know that in order traversal if you apply for the given binary tree, there are so many combinations are possible, okay? So for given in order traversal, how many binary trees you can construct means 1 by n plus 1 into 2n which is Catalan number which we discussed in the class. Suppose if they provide only in order traversal, how many binary trees you can construct 1 by n plus 1 into n. If they provide only pre-order traversal, how many you can construct 1 by n plus 1 into 2n binary trees possible. Only if they provide post-order traversal will have same binary trees. It means that unique binary tree is not possible by using alone in order traversal. By using alone post-order traversal, it is not possible to get unique binary tree. By using only alone pre-order traversal also, it is not possible to get unique binary tree. In such case, if you want to get unique binary tree, make the combinations. What are the combinations? In order and pre-order you can use, or you can use in order and post-order, provided that if they ask binary tree. If they ask full binary tree, it is compulsory you have to take any of the two, like in order pre-order, in order post-order, and in pre-order and post-order like this, okay? So I hope this concept is clear. Next, a complete binary tree with n internal nodes have n plus 1 leaf nodes they are asking. N internal nodes have n plus 1 leaf nodes. It is regarding complete binary tree. Just check whether are you understanding this question or not. A complete binary tree with n internal nodes having n plus 1 leaves. See, we can prove mathematically, or you can take simple example to prove this statement. For example, if you take complete binary tree, it is a complete binary tree. How many internal nodes are there here? One internal node. But how many leaf nodes are there? Two leaf nodes are there, right? Two leaf nodes. Let me consider one more. So it is also complete binary tree, right? Complete binary tree means all levels are full except possible last level filling from left to right. How many internal nodes are there? 1, 2, 3. And how many leaf nodes are there? 4 leaf nodes. So 3 internal nodes, 4 leaf nodes, n internal nodes, n plus 1 leaf nodes, satisfied. And another example, complete binary tree. So it is also complete binary tree, friends, because complete binary tree filling from left to right. Now verify how many internal nodes here. There are 2 internal nodes. But how many leaf nodes are there? Only 2 leaf nodes. So here they mention n internal nodes, n plus 1 leaf nodes. But we have 2 internal nodes, 2 leaf nodes only. Hence I can say this statement is false. Okay, this statement is false. So a tree with it's having n minus 1 edge is correct, and it is not correct because they are talking about binary tree can be constructed uniquely by using post order pre-order is not possible. But if they ask full binary tree, yes, it is correct. If they ask full binary tree, it is correct. Next, the maximum number of nodes in a binary tree having height h equal 2 power h plus 1 minus 1. Yes, we already proved this one, right? Okay, so it is also correct. Yeah, this is actually general question based on binary tree concept. Okay, just read the question. I hope you already done this problem. Okay, I'll explain if you want. Consider the following nested representation of binary tree xyz. xyz is a nested representation where y and z are the left and right subtrees respectively, and further y and z may be null or they may be further nested. Y and z may be further nested. Okay, then which of the following represents valid binary tree? See, the basic idea of this question is, if you take parenthesis x, y, z, where x indicates parent, where y comma z are left and right subtrees. So it is looking like this: x is a parent, where y representing left subtree and z also representing right subtree. So this is a structure of the given tree, right, friends? Okay, so it is y and it is z. Then what about the other characteristic about y and z? Y may be further nested. Y may be further nested. Further nested means compulsory it must have 3 elements. 3 elements. Okay. Z may be further nested. Further nested means it may have 3 element structure. Right, friends? Okay. So in that case, suppose if y and z are further nested, what is the pattern it is having? If y and z are further nested, we can write like this: if x is a root node parent and y is further nested, it must have 3 more elements like this. Okay, 3 more elements. Then we can say y is further nested. and Z is also further nested, then Z also having 3 more elements. So this is a case we can say Y and Z may be further nested. Let me check which is satisfying in this case. See here, you consider X and you consider Y, you can consider Z. X is satisfying properly, Y also satisfying properly, but Z is further nested means maximum how many elements are allowed? Not maximum, exactly how many elements are allowed? 3 elements. But how many we are having? It is X, it is Y, it is Z, but what about 7? Right, it is invalid, therefore ignore this. Now in this case you can consider it is X, this total part whatever we are calling it is Y and it is called Z. So X is properly defined, Z is properly defined, Y is further nested. If it is further nested, then you can consider it is X, you can consider it is Y, it is Z. But inside that again X is further nested, X cannot be further nested, only Y or Z may be further nested. Therefore this pattern is not available. Okay, X cannot be further nested, only Y and Z may be further nested. Therefore you can ignore this one. Next, whatever this one, it is X, it is Y, and you can take it as Z. Y is further nested, so we can take X, Y, Z. Yes, it is properly defined. Z is further nested, we can say X, Y, Z, which is also properly defined. Next, if you consider it is X and you can consider it is Y, it is Z. So again Y is further nested, so X, Y, Z. They also mention that Y and Z may be null. Therefore, it is valid, it is also valid. But it is not valid because if it is further nested, compulsory 3 elements are there. X is required, Y is required, Z also required, but Z is missing. That's why this is not the correct answer. Okay. Hence, option C is the correct answer for this question. Clear, friends? Okay. I hope most of you understood this problem. The same question, level order traversal of a rooted tree can be done by using root and performing. Actually, level order traversal is nothing but BFS, breadth first search. Okay. So breadth first search we are calling level by level, that is called level order traversal, that we will discuss in graphs. Next, this question is related to array concept, array representation of binary tree. Okay. You also read the question, simultaneously draw the diagrams. By using questions, I am able to revising all the concepts, friends. Okay, it's the best approach for revising concepts. So in the array representation of binary tree, any binary tree, either binary tree or complete binary tree or full binary tree, what it may be. In the array representation of binary tree, they are using root node indexes starting from 1 instead of 0. Root node index is starting from 1 instead of 0. Therefore, I am taking root node index is 1. Right, friends. For any left child, its index is 2i. Right child, they are taking 2i plus 1, that is equal to 3. Here it is 4, 5, 6, 7 like this. So they are storing these elements into the array where root node index starting from 1. So 1, 2, 3, 4, 5, 6, 7. Therefore, A will be stored into first index, B will be stored into second index, C will be stored into third index. Next, D, E, F, G. D, E, F, G. Clear, friends? Okay. In this case, what did they ask? For any node, just observe. For a node which is stored at index xi, the left child, if anyone is existing, it is stored at x of 2i, and right child, if anyone is existing, it is storing at x of 2i plus 1. Clear? X of 2i plus 1. What does it mean? For example, if I consider I equal to second index, friends, okay, I equal to second index. What about its left child? Left child is equal to 2i. That's what they are saying. 2 into 2, that equal 4. What about right child? Right child is equal to 2i plus 1. This value equals to 2i plus 1. Therefore, in general, the representative is, if you take any tree, suppose node x, if it is at ith index, its left child y at 2i, right child z at 2i plus 1. That's what they are discussing. Okay. And the parent of this node, something like A must be at floor of I by 2. Floor of I by 2. For example, if I consider 3, who is a parent of index 3? That equal to index 1. Therefore, floor of 3 by 2 that equal to 1.5. Floor of 1.5 means 1. If you take 2, parent index equal floor of 2 by 2 that equals to 1. Right friends? This condition must and should hold. Now, what did they ask question? To be able to store binary tree on n vertices, the minimum size of the array they are asking. The minimum size of the array. So, what is the minimum size of the array? So, whenever they are talking minimum size of the array, you have to take all types of trees. To be able to store any binary tree they are asking, right? Any binary tree. Now, can you post your answer for this question? Actually, in the options, there are some corrections are required. It is not 2n, 2 power n plus 1. It is 2 power n minus 1. It is log n based. Since they are using the word is to be able to store any binary tree, to be able to store any type of binary tree, therefore you take all types of binary trees, friends. Okay. For example, if you consider left skewed binary tree x, y, z with 3 nodes, and with 3 nodes, full binary tree is looking like this: x, y, z. With 3 nodes, right skewed binary tree is looking like this: x, y, z. When you start indexing these elements, root node index is starting from 1, left child 1 into 2, 2, 2 into 2, 4. These are indexes. Therefore, the array structure is looking like this, like 1, 2, 3, 4. So, who is sitting first index? X. Who is sitting second index? Y. Third index is obviously it is null. Okay. And fourth index is it equals to Z. So, for 3 nodes, size of the array is equal to n plus 1. For 3 nodes, size of the array equal to n plus 1 in this case. Okay. So, if I take it is 1, 2, 3. First index, second index, third index. That is x, y, z. For 3 nodes, size of the array is equals to 3 now. Now, if root node index is 1, right child 2 into 1, 2, and right child again, 2 into 2 plus 1. Right child index is 2i plus 1 that equal 3, 2 into 3 plus 1 that equal 7. Because the question they mentioned, right, for any index I, right child must be at x of 2i plus 1. Therefore, 2 into 3, 6 plus 1, 7. Right. So, to store this binary tree, we need how many locations? 7 locations. 1, 2, 3, 4, 5, 6, 7. That equal I can say x first location, y third location, and z at the 7th location. Remaining all are empty locations, null. It means that total how much size is required? 7 is required. Since they mentioned to be able to store any binary tree, therefore I cannot say n plus 1. I cannot say n, right friends, okay? Because if you take n plus 1, it is not possible to store this binary tree, okay? So therefore, it is not possible to take n plus 1, it is not possible to take n. So therefore, answer is 2 power n minus 1. If n is equal to 3, 2 power 3, 8, 8 minus 1 that equal to 7 locations are required. Therefore, answer is 2 power n minus 1. So option D is the correct answer. To be able to store any binary tree, we have to use 2 power n minus 1, friends, okay? Yeah. Just think about this problem. In this question, again it is using same formula which I explained earlier. Apply the same formula which I explained here. So, see the number of internal nodes of degree 1 is equal to 5 they mentioned. Number of internal nodes of degree 1 is 5. Suppose number of internal nodes of degree 1 we are defining it is I1. Earlier we discussed this problem, right? Okay. Number of internal nodes of degree 2 is 10. So, degree 2 means we can take it as I2. Degree 2 means I2. And the number of leaf nodes they are asking now, right? Number of leaf nodes. We have one formula, total number of nodes, internal nodes I1 plus I2 plus leaf nodes. Have you remembered this formula? Total number of nodes is equals to, means internal nodes plus leaf nodes is equals to I1 internal nodes, right? I1 internal nodes of degree 1, right? How many internal nodes are there? That is 5 internal nodes. So, number of internal nodes of degree 1 is 5. Let me take here I1 internal nodes of degree 1 plus I2 internal nodes of degree 2 plus 1. This is what we discussed earlier, right friends? Okay. Here I1 indicates that 5 internal nodes and I2 indicates that 10 internal nodes. We want to find leaf nodes is equals to 5 into 1 plus 10 into 2 plus 1, right friends? Okay. So from this it is 15, here it is 25 plus 1, 26. So therefore number of leaf nodes equals 26 minus 15, that equals to 11 leaf nodes. This formula I already explained earlier. Total number of nodes is equals to number of internal nodes of degree 1 plus number of internal nodes of degree 2 plus k, sorry, plus 1. Yeah, this question asks max number of nodes of a binary tree. So max number of nodes of binary tree, which we already covered, 2 power h plus 1 minus 1 friends. Okay. The properties of binary tree, max number of nodes of a binary tree equal to 2 power h plus 1 minus 1 is the answer. Okay. See the maximum number of binary trees that can be formed with the 3 unlabeled nodes. Whenever they are asking unlabeled nodes or labeled nodes, we can say n 1 by n plus 1 into 2ncn for unlabeled nodes. For unlabeled nodes. Therefore, substitute n is equal to 3 here, 1 by 3 plus 1 into 2 into 3, that equals 63, which equal 1 by 4 into 63 value equal 20, that equal to 5. So answer to this question is 5 is the correct answer. Okay.